In this video, we will explore decision trees, a fundamental algorithm in machine learning. It is widely used for classification and regression tasks due to its simplicity and interpretability. Before diving in, let's first understand its history. '60s, early concepts. The roots of decision trees trace back to early work in statistics and AI. Researchers explored rule-based systems for decision-making. 1970s to 80s, ID3 algorithm. Ross Quinlan developed the ID3 algorithm. ID3 introduced information gain to decide the best splits. 1990s, C4.5 and CART. Quinlan improved ID3 into C4.5, handling missing values and continuous data. CART, classification and regression trees, also emerged, using Gini impurity. 2000s present, ensemble methods. Random forests and gradient boosting improved decision trees. These methods enhanced performance by combining multiple decision trees. Root node. The root node is the topmost node of the decision tree. It represents the entire dataset before any splits are made. Internal nodes. Internal nodes, also known as decision nodes, are where the dataset is split based on a feature. Each node represents a decision or test condition, such as, is the temperature greater than 30 degrees Celsius? Single quote. Branches, or edges, are the connections between nodes. They represent the possible outcomes of a decision. Leaf nodes. Leaf nodes are the final nodes in the decision tree. They provide the classification label or regression value. Decision stump. A decision stump is a simplified decision tree with only one split. It consists of a root node and one level of branches. Pure leaf. A pure leaf is a leaf node where all data points belong to the same class. For example, if all data points in a leaf node are labeled as play tennis, it is a pure leaf. Impure leaf. An impure leaf is a leaf node containing data points from multiple classes. For example, if a leaf node has some data points labeled, play tennis, and others labeled, don't play tennis, it is an impure leaf. Splitting. Splitting is the process of dividing a node into two or more subnodes based on a feature. The goal is to create subsets of data that are more homogeneous in terms of the target variable. Tree depth. Tree depth refers to the number of levels in the decision tree. A deep tree has many levels and can capture complex patterns in the data. But it may also overfit. Pruning. Pruning is the process of removing branches from the tree to prevent overfitting. Overfitting occurs when the tree becomes too complex and captures noise in the data. Feature importance. Feature importance ranks features based on how much they contribute to decision making in the tree. Features that are used to split the data at higher levels of the tree are considered more important. Parent node. A parent node is a node that has one or more child nodes. It represents a decision or split that leads to further subdivisions of the data. Child node. A child node originates from a parent node. It represents the outcome of a decision made at the parent node. Siblings. Siblings are nodes that share the same parent node. They represent different outcomes or branches resulting from the same decision. Subtree. A subtree is a branch of the decision tree that forms a smaller tree within the main tree. It can be treated as an independent decision tree. Voting. Ensemble trees. In ensemble trees, such as random forests, multiple decision trees are combined. The final prediction is made through majority voting. For classification, or averaging. For regression. Entropy and Gini index. Two important measures used in decision trees to determine the best feature for splitting a dataset. Entropy measures the level of disorder or impurity in a dataset. It is calculated using the formula. Here, S is the dataset, C is the number of unique classes, and Pi is the proportion of instances that belong to class I. Let's break this down step by step. The term Pi represents the probability of a randomly chosen instance belonging to class I. The logarithm base 2 of Pi measures the information content of that class. Multiplying by Pi and summing over all classes gives the expected information content of a dataset. When all instances belong to a single class, Pi is 1 for that class, and the entropy is 0, indicating no disorder. When the dataset is evenly distributed across classes, entropy is maximized, indicating maximum disorder. The Gini index measures the probability of misclassifying a randomly chosen instance if it were randomly labeled according to the class distribution. Its formula is, here, Pi is the proportion of instances in class I. The Gini index is minimized when all instances belong to a single class, and maximized when the dataset is evenly distributed across classes. Both entropy and Gini index are used to determine the best feature for splitting the dataset. Lower values indicate purer subsets. Let's consider a simple dataset called play tennis to understand these concepts. First, let's calculate the entropy for the entire dataset. There are 9 feet yes and 5 no out of 14 samples. The probability of yes is 9/14 and for no is 5/14. Now, applying the entropy formula. Let's compute the logarithms. Log base 2 of 9/14 is approximately minus 0.64. And log base 2 of 5/14 is approximately minus 1.48. Substituting these values, we get, which simplifies to approximately 0.94. Now, let's calculate the Gini index for the entire dataset using the same probabilities. Calculating the squares, 9, 14 squared is approximately 0.412, and 5, 14 squared is approximately 0.127. So, Gini S equals 1, 0.412 plus 0.127 equals 1 minus 0.539 equals 0.461. Now, let's see how we can split the dataset based on the weather feature and calculate the entropy for each subset. The weather feature has 3 categories: sunny, overcast, and rainy. Let's group the data accordingly. For the sunny group, there are 5 samples, 2 feet yes and 3 no. Let's calculate its entropy. For overcast, all 4 samples are yes, so the entropy is 0. For rainy, there are 5 samples, 3 feet yes and 2 no, so its entropy is also approximately 0.971. Now, the weighted average entropy after splitting is calculated as follows. Substituting the values, we get approximately 0.693. The information gain is the difference between the original entropy and the weighted average entropy. 0.94 minus 0.693 equals 0.247. In conclusion, entropy and Gini index are crucial for building decision trees. They help in selecting the best feature to split the data. Aiming for purer subsets, lower entropy or Gini index indicates better splits. A decision tree classifier is a supervised learning algorithm used for classification tasks. It models data in a tree structure, where each internal node represents a decision based on a feature. Each branch represents an outcome of that decision, and each leaf node represents a final class label. The decision tree algorithm works by recursively splitting the dataset into subsets based on feature values. The goal is to create subsets that are as pure as possible, meaning that the majority of the instances in each subset belong to the same class. To determine the best feature to split on, the algorithm uses criteria like Gini impurity or entropy. Gini impurity measures the likelihood of incorrectly classifying a randomly chosen element, while entropy measures the disorder or impurity in the dataset. Information gain is used to decide which feature to split on. It calculates how much entropy is reduced after a split. The feature with the highest information gain is chosen for the split. To prevent overfitting, decision trees use pruning techniques. Pre-pruning stops the tree from growing further when certain conditions are met, such as reaching a maximum depth or having too few samples in a node. Post-pruning, on the other hand, grows the full tree first and then removes branches that do not improve accuracy. Let's consider a simple dataset about whether a person will go jogging based on weather conditions. First, let's calculate the entropy for the entire dataset. There are 8 feet yes and 6 no out of 14 samples. The probability of yes is 8/14 and for no is 6/14. Now, applying the entropy formula. Let's compute the logarithms. Log base 2 of 8/14 is approximately minus 0.81. And log base 2 of 6/14 is approximately minus 1.22. Substituting these values, we get, which simplifies to approximately 0.99. Now, let's calculate the Gini index for the entire dataset using the same probabilities. Calculating the squares, 8, 14, squared is approximately 0.326, and 6, 14, squared is approximately 0.184. So, Gini S equals 1, 0.326 plus 0.184 equals 1 minus 0.510 equals 0.490. Now, let's split the dataset based on the outlook feature and calculate the entropy for each subset. The outlook feature has 3 categories: sunny, overcast, and rainy. Let's group the data accordingly. For the sunny group, there are 5 samples, 2 feet yes and 3 no. Let's calculate its entropy. For overcast, all 4 samples are Yes, so the entropy is 0. For rainy, there are 5 samples, 2 feet yes and 3 no, so its entropy is approximately 0.971. Now, the weighted average entropy after splitting is calculated as follows. Substituting the values, we get approximately 0.69. The information gain is the difference between the original entropy and the weighted average entropy. 0.99 minus 0.69 equals 0.30. In conclusion, decision trees use entropy or Gini index to determine the best feature for splitting the data. This process is repeated recursively to build the tree, aiming for the purest subsets. A decision tree regressor is a supervised learning algorithm used for regression tasks. It models data in a tree structure, where each internal node represents a decision based on a feature. Each branch represents an outcome of that decision, and each leaf node represents a predicted value, typically the mean of the target values in that leaf. The decision tree algorithm for regression works by recursively splitting the dataset into subsets based on feature values. The goal is to create subsets where the target values are as similar as possible, meaning that the variance of the target in each subset is minimized. To determine the best feature to split on, the algorithm uses the variance reduction criterion. The variance for a subset is calculated as the average squared difference from the mean. To prevent overfitting, decision trees use pruning techniques. Pre-pruning stops the tree from growing further when certain conditions are met, such as reaching a maximum depth or having too few samples in a node. Post-pruning, on the other hand, grows the full tree first and then removes branches that do not improve the error on a validation set. Let's consider a simple dataset about rainfall amounts based on weather conditions. First, let's calculate the variance for the entire dataset. There are 14 samples with rainfall values ranging from 1 to 22. The mean rainfall is approximately 11.43, and the variance is approximately 58.97. Now, let's split the dataset based on the outlook feature and calculate the variance for each subset. The outlook feature has 3 categories: sunny, overcast, and rainy. Let's group the data accordingly. For the sunny group, there are 5 samples with rainfall values 2, 3, 1, 4, 2. The mean is 2.4, and the variance is approximately 1.04. For overcast, there are 4 samples with rainfall values 10, 12, 11, 13. The mean is 11.5, and the variance is 1.25. For rainy, there are 5 samples with rainfall values 20, 22, 19, 21, 20. The mean is 20.4, and the variance is approximately 1.04. Now, the weighted average variance after splitting is calculated as follows. Substituting the values, we get approximately 1.1. The variance reduction is the difference between the original variance and the weighted average. Variance 58.97 minus 1.1 equals 57.87. In conclusion, decision trees for regression use variance reduction to determine the best feature for splitting the data. This process is repeated recursively to build the tree, aiming for subsets with minimal variance. The first advantage is that decision trees are easy to understand and interpret. The tree structure is intuitive and mimics human decision making. However, a major disadvantage is that decision trees are prone to overfitting, especially when the tree becomes too deep and complex. Another advantage is that they can handle both numerical and categorical data without requiring extensive preprocessing. On the other hand, decision trees can be unstable. Small changes in the data can lead to very different tree structures. Decision trees also require little data preparation compared to other algorithms, for example. They don't need feature scaling. Additionally, decision trees are biased towards features with more levels or categories, which can affect the splits. Finally, decision trees can capture nonlinear relationships between features, which is useful for complex datasets. Lastly, they are not great for extrapolation, meaning they may perform poorly on data outside the range of the training set. I hope you found this video helpful. If you enjoyed it, please give it a thumbs up, subscribe to the channel, leave a comment, and share it with your friends. Your support means a lot. See you in the next video.